All right, you guys, this is your week 11 wrap-up video. I have been behind on these wrap-ups, but I figured they'd be a good review for the final. And so this one was on alcohols, esters. I think there's some thiols in here. Okay, so we'll take a look at those. So some of you guys were had questions about this question, and it was in the naming alcohol section. It says give the IUPAC name for the following compound shown here. These were the options you had. So remember with the alcohols, there are OH group that indicates the alcohol. That indicates that we need an OL ending. So all of these have OL ending, so they could potentially all be correct, right? And remember, we always want to look for the longest chain of carbons that contains the alcohol. So here's an alcohol here, and alcohol here, and there's 1, 2, 3 carbons. So we know that this is going to be a prop. And so we have prop in all these names, but we also have a second alcohol group here in the middle. And so we need to tell kind of our audience where that is. And so we have the alcohol on carbon 1 and then alcohol on carbon 2. So the correct name for this one is 1, 2. Again, we're numbering the carbons from right to left. We always want to give our functional groups the lowest numbers possible. So this is 1, 2 propane, and then diol. This di here tells us that there's 2 prefixes here. Okay, so that is how we would name that compound. You guys have questions on this one? Okay. Again, we have that OH functional group telling us that this is an alcohol. We need an OL ending. Notice here on your options, only 2 of the possible choices out of the 4 have an OL ending. So that kind of can help guide your decision making. That would get harder if you have multiple types of functional groups on the same compound. But here, you know, the alcohol is present and everything else is, you know, just single bond. So the alcohol takes highest priority. So it should have that OL ending. So we know it's not the second choice or the 4th choice. And then we have, there's a methyl group, and we're assuming that alcohol group, if it's a substituent on a ring, that is occurring, that is carbon number 1, wherever that substitution is happening. And so here we have 1-methyl cyclopentanol. We don't need to indicate that the OH is on carbon 1. Like I said, it is assumed that it is on carbon 1. These are 5 carbons in a ring, so that's a cyclopentane. And again, we're going to change the N to OL because we have alcohol, cyclopentanol, and we only need to indicate, you know, the location of the methyl group. So just the 1 is what we need. This is a little tricky. I wouldn't do this to you on a test, but just to see if you're paying attention in the content about that. If this methyl group wasn't there, so let's say the CH3 group wasn't there, then we could call this cyclopentanol with the OL ending. Again, questions you guys had about this were reactions that form alcohols. And the main one you should know about is the hydration. And look at the word, it's hydration. Doesn't it make you think of hydrate? And so when you think of hydration, you need water, right? So you can hydrate across a double bond. So we've seen this reaction when we were looking at the alkenes. So you can take an alkene, you can add water, and if you think of the water, instead of thinking of it as H2O, think of it as HOH. One of the hydrogens is going to go to one of the carbons in the double bond, and the OH group is going to go to the other carbon of the double bond. And then we get our alcohol. So here's an example, kind of what you see right above, but ethylene plus water. Again, 1 carbon in the double bond gets the H and the other one gets the OH, and we have ethanol. So hydration of alkene is kind of the most important one you should know for a reaction that makes an alcohol. There is something called Markovnikov's rule, okay? And so the rule says that if you consider water to be this HOH, the hydrogen atom of the water is going to go to the carbon atom that has the most hydrogen, and the OH group goes to the carbon with the fewer hydrogen atoms. What does this mean? Okay, so if we look at this molecule, this propylene, we can see here's a double bond. This is one of the carbons involved. This is the other carbon involved. This carbon has 2 hydrogens. This carbon only has 1. So when we go to hydrate that double bond, the H of water is going to go to the carbon that has more hydrogens. So this had 2 hydrogens, this had 1. So our hydrogen is going to go to this carbon on the end. So you can see it went from CH2 to CH3. Then the OH group is going to go to the other carbon of the double bond. It had less hydrogens. So then you end up with a 2-propanol. Okay. So that's a little kind of thing to know when you're doing this hydration of double bonds. So you can know what the products are. Another reaction that was talked about in the, it wasn't this complicated, and it's not going to be this complicated for you guys, but in the formation of alcohols was fermentation. This is can happen, with microorganisms. And basically, whenever we're like, just like in the when we're making alcohol, you break down sugars through glycolysis and you get pyruvate, and then from pyruvate you can decarboxylate, so you remove a carbon dioxide group. You end up with this acetaldehyde, and more importantly is that you can reduce this acetaldehyde to ethanol. Okay, so you do not need to I don't plan on testing you on this, but it did come up on your top hat content that fermentation was a way to form alcohol. Of course, you guys can think of like when people make beer or any other distilled spirits, that there's a fermentation process. And it's in this case, we're showing the reduction from acetaldehyde to ethanol. Okay, so that's just something interesting. Okay. So then reactions of alcohols, and then on this title it says phenols too. Remember, alcohols and phenols react pretty differently, because we'll look at phenols in a minute, but phenols have different properties because remember, it's a OH, a hydroxy group, but it's attached to an aromatic ring. Okay, so let's just focus on the alcohol part here. So we can do a dehydration. So this is the exact opposite of what we just saw about the formation of alcohols. Instead of adding water across a double bond, we can remove a water molecule from alcohol and get the alkene. Now, remember just a couple slides ago, we just saw it the other way, right? We saw we were adding water across the double bond and getting the alcohol. Well, we can go the other way. And it's in this case, it's called a dehydration because we're removing water. We're dehydrating it. So we just remove the OH group and a hydrogen from a neighboring carbon, and they'll form a double bond. So that is one you should be familiar with. Dehydration of an alcohol gives you an alkene. Okay. Here's some examples. Here's ethanol. Remove a OH group from one carbon and a hydrogen from another, and you get ethylene. Again, and I like to show you guys because this gives you a different way of looking at it. So just in case you see it different ways. Okay. And again, like I said, phenols cannot be dehydrated. They're different, right? So phenols are not going to be dehydrated. This is not a phenol. Okay. This is OH group attached to a 6-membered ring. Okay, so a cyclohexane. So you could remove an OH group and a hydrogen here and get a double bond, okay, depending on which hydrogen you remove. There's different products possible based on whether you have a primary, secondary, tertiary alcohol, but I'm not going to assess you guys on that, so you don't need to worry about that. And again, phenols cannot be dehydrated. Okay, oxidation was another reaction that we looked at. And remember, we have lots of different ways to define oxidation. Loss of electrons we define as oxidation. Another way is like gain of bonds to hydrogen, or gain of bonds to oxygen, and then loss of hydrogen. Those are all different bonds. And you don't have to do all of them to satisfy oxidation. It's just those are the different definitions that at least help me recognize when oxidation is occurring. So for instance, in this example, you're going from an alcohol to aldehyde. this carbon has one bond to oxygen, and then going from the alcohol to the aldehyde, that carbon gains a bond. So now it has a double bond to this oxygen. So that is an oxidation. Notice the functional group. We went from an alcohol and we ended up with a carbonyl. In this case, it's an aldehyde. Remember, if the carbon of a carbonyl is attached to a hydrogen, that's an aldehyde. Notice this is a primary alcohol, meaning the OH group is connected to a carbon, and that carbon is attached only to one other carbon. That's a primary alcohol. This changes in secondary alcohol. So again, the OH group is attached to this carbon. This carbon right here is attached to two other carbons, so that gives us the secondary alcohol. If we oxidize this, we end up with a ketone. Remember, a ketone is when the carbon of a carbonyl is attached to two other carbons, as it is here with the secondary alcohol. Here, this is a tertiary alcohol. Again, the OH group's attached to this carbon. That carbon's attached to 1, 2, 3 carbon molecules. And when you oxidize this, you actually get no reaction, right? There isn't a hydrogen to pull off. And so tertiary alcohols do not undergo oxidation. So oxidation of an alcohol, if it's primary, you get an aldehyde. Secondary, you get a ketone. Tertiary, no reaction. Okay, so you guys had this question on your homework. I'm going to get a drawing tool out to see. So 2 molecules of compound Y with a molecular formula C4H10O. So you have 2 of these, right? So C4H10O. And you actually have 2 of them. C4H10O is converted to 1 molecule of Z. So these combine and you get Z, and it has C8H18O. It wants you to figure out, did it get oxidized, reduced, dehydrated, or neither? Okay, let's see what happened, right? If we took 2 of these and we have 4 carbons here, 4 carbons here, we should have 8 here, and we do. Okay, so all our carbons made it into the product. Our hydrogens, we have 10 here and 10 here, so we have 20 altogether, but we only have 18 in the product. That means we lost 2 hydrogens. So I'm going to say along this way we lost 2 hydrogens. I'll put it 2. And then we have an oxygen here and an oxygen here, so we had 2 oxygens to start with, but in our product we only have 1. So we lost an oxygen. So we lost 2 hydrogens and we lost an oxygen. We lost the H2O. We lost a water molecule. If we lose a water molecule, that is a dehydration. So it got dehydrated would be the correct answer here. So then phenols, like we've been talking about alcohols. Remember, alcohols is when an OH group called the hydroxyl group is attached to an alkyl, meaning like a carbon chain. Okay, a phenol is when you have an OH group or this hydroxyl group attached to an aromatic ring. Remember, aromatic ring has alternating single and double bonds. It's not just simply cyclic. Okay, it's important that it has those alternating single and double bonds. So that is the definition of a phenol. All right, so the other functional group we looked at in this week 11 content was ethers. Ethers are simply if you have an oxygen molecule, okay, and it has a single bond to 2 carbons. So this oxygen is single bonded to this carbon here and single bond to that carbon there. That's an ether. So it's like an oxygen molecule in between 2 carbons is another way to think of it. So like this oxygen has this carbon of this cyclic ring over here, and then this carbon, this group here. This oxygen is attached to this carbon and this cyclic ring, and this carbon and this cyclic ring. So those are both considered ethers. Hey. Okay. So if you predict the structures of the following ethers, okay? So So you can tell, again, we won't do much naming. We won't get too complicated because it can get way too complicated when we start getting to all these functional groups. But like this says diethyl ether. You should know that di means two. You should know that an ethyl group contains two carbons. So it's two carbon groups. So ethyl group here, ethyl group here. If it's an ether, that means there's an oxygen stuck in between them. Methyl propyl ether. Okay, methyl is a one carbon group. Propyl is a three carbon group. If it's an ether, there's an oxygen stuck in between them. Cyclohexyl is this 6 carbons in a ring. Ethyl is a 2 carbon group. Again, it's an ether. There's an oxygen stuck in between them. Phenyl, so see how this is a phenyl group and a propyl group, so 3 carbon group. Again, it's an ether. There's an oxygen stuck in between them. And then this is a common name that's really popular still. I won't test you on this, but just make you aware of it, expose you to it. 5-membered ring, oxygen in the middle. So this is technically an ether, right? But the common name for this is tetrahydrofuran, sometimes called THF. Okay. All right, and then in aldehydes, we also looked at aldehydes. And so you had to give the IUPAC name for the following compound. So remember, the aldehyde functional group is when you have this C double bond O, which is a carbonyl, and then the carbon of the carbonyl is attached to a hydrogen. And so that's your aldehyde. And we want to count the longest carbon chain. So that's 1, 2, 3, 4. So that's 4. So that's a bute. Okay. So I know this says hexanol, and I put that in there because there's 6 carbons. But remember, we need the longest continuous chain. That's 4. So it's one of these. We want to give the aldehyde the lowest number. So this is 1, 2, and 3. So this is carbon 3. And so we have a methyl group and a second methyl group attached to carbon 3. So this actually becomes 3,3-dimethyl butanol. And look, notice I have this second choice, this 3,3-dimethyl butanol, right? Notice the ending, OL, that would be for alcohol, an OH group. Remember, AL tells us aldehyde. And maybe some of you thought it might be 2,2 because if you started counting from the left, but we got to give the aldehyde the lowest carbon. So this is carbon 1, this is carbon 2, this is carbon 3. Some properties of aldehydes. Again, remember, it has that carbonyl. And with that carbonyl, you get this unequal sharing of electrons. So the oxygen has that partial negative charge. The carbon has a partial positive charge. You get this dipole. With the properties, again, as the carbon part of the aldehyde gets bigger, the polarity is going to play less of a role. So polarity is going to decrease, and that means also water solubility is going to decrease. Okay. So the smaller aldehydes can be water soluble, bigger aldehydes are not. Okay. Again, in aldehydes, they can act as a hydrogen bond acceptor, meaning that oxygen of the carbonyl here can hydrogen bond with hydrogens of water, but there's no hydrogen bonding happening in an aldehyde because there's not a hydrogen attached directly to fluorine, oxygen, or nitrogen. Okay. And then look at these boiling points. As the boiling points, again, as the number of carbons increase, the boiling point goes up. But notice the boiling points are smaller than those of alcohols. Okay. For ketones, remember ketones is when you have a carbonyl, so a carbon double bonded to an oxygen, and the carbon of the carbonyl is bonded to two other carbons. Same thing, small ketones are water soluble, but as you get more and more carbons on there, the polarity is going to go down. And so those larger ketones are not going to be water soluble anymore. And same thing as the aldehyde, it can act as a hydrogen bond acceptor with water, okay? But there's not going to be any hydrogen bonding going on between ketone molecules. So no intermolecular hydrogen bonding. Again, because there's not a hydrogen directly bonded to an F, O, or N. Oh, and then we had thiols. Thiols contain sulfur. So if you have this SH group attached to, an alkyl group, a carbon group, that's considered a thiol. And what you need to know, here's the physical properties. So they have lower boiling points than alcohols, because there's less polarity, and they tend to be soluble in non-polar solvents. Okay, so even when they're small, they tend to have little solubility in water. And this is kind of the most relevant reaction with thiols, especially when we get to the biological chemistry, to the biochem part, is that if you oxidize a thiol, you get what's called a disulfide. So maybe you guys have heard of this disulfide bridge in proteins. And you can do the opposite. You can take that disulfide and you can reduce it and you can get 2 thiols back. Okay, so you'll see this is has a lot of importance when we're talking about protein structure and formation of tertiary structures, and this is like an alpha helix. So they can help hold that shape. Okay, that's it. I will stay strong and keep studying, guys.